In this lab, I will simulate an intrusion using a reverse TCP Meterpreter session. After the session is opened, I will trigger a Sentrix Shield Honeytoken. Later, the Honeytoken alert can be investigated using email logs. Before starting, both virtual machines must be able to communicate with each other. For this lab, both machines are connected to the same VirtualBox NAT network. Kali Linux is using the IP address 10.0.2.4. The Windows target machine is using the IP address 10.0.2.15. Because both machines are on the same lab network, the reverse TCP connection can work. A reverse TCP payload works by making the target machine connect back to the attacker machine. This means Kali must listen for the incoming connection. The Windows machine will connect back to Kali. The Kali IP address will be used as lhost in Metasploit. A common mistake is using the Windows target IP as lhost. That is incorrect. Lhost must be the reachable IP address of the attacker machine. In this lab, the correct lhost is 10.0.2.4. Next, I confirm the Kali IP address from the terminal. I can see that Kali is connected to the lab network. Then I check the Windows IP address using PowerShell. The Windows VM is also connected to the same lab network. Now I test whether the Windows machine can reach Kali on the listener port. I start a simple listener on Kali. Then I test the connection from Windows to Kali on port 4444. The connection test succeeds. This confirms that the reverse TCP path is working. Now I can start Metasploit on Kali. Inside Metasploit, I use the multi-handler module. The multi-handler waits for an incoming reverse connection. I configure the handler to use a Windows 64-bit Meterpreter reverse TCP payload. The payload type must match the payload that will be generated later. I set lhost to the Kali IP address. In this lab, lhost is 10.0.2.4. I set lport to 4444. This means Kali will listen on port 4444. I also set exit on session to false. This allows the handler to continue running after a session opens. I review the handler options to make sure everything is correct. The payload is correct. The lhost is correct. The lport is correct. Now I start the handler. Metasploit is now waiting for the Windows VM to connect back. Next, I generate the Windows payload using MSF Venom. The payload is a Windows 64-bit Meterpreter reverse TCP executable. I use the same lhost and lport as the Metasploit handler. The lhost is 10.0.2.4. The lport is 4444. I save the payload as reverselab.exe. This file is created only for this controlled lab environment. The handler and the payload must match exactly. If they do not match, the session may not open. Now I transfer the payload to the Windows virtual machine. For this lab, I use a simple Python web server on Kali. The web server is bound to Kali's lab IP address. On the Windows VM, I download the payload from Kali. I save the payload to the desktop of the Windows user. This is a simple file transfer method for a private lab network. In a real security assessment, payload delivery must follow the approved rules of engagement. Now I manually run the payload on the Windows virtual machine. This simulates the execution stage of the intrusion. Because this is an educational lab, I execute the file directly on my own test machine. Once the payload runs, the Windows VM connects back to Kali. Back in Metasploit, a Meterpreter session opens. This confirms that the reverse TCP connection worked successfully. Now I list the active Metasploit sessions. I can see session number 1. The session type is Meterpreter for 64-bit Windows. The session belongs to the Windows user John. The connection shows Kali listening on 10.0.2.4, port 4444. The Windows target is connecting from 10.0.2.15. This means the intrusion simulation was successful inside the lab. Now I interact with session number 1. Now I move to the Windows machine and open Sentrix Shield. Inside Sentrix Shield, I go to the Honeytokens section. This is where I can generate a new decoy file. For this test, I create a new Honeytoken with a realistic file name. I name the Honeytoken Q4 2026 Finance Report. The goal is to make the file look like a normal business document. This file is only a decoy. It does not contain any real sensitive information. Next, I choose the location for the Honeytoken. I save the file on the desktop of the Windows user John. The location is C users John desktop. I also enable monitoring for file actions. I enable monitoring for open actions. I enable monitoring for copy actions. I enable monitoring for remove actions. Now I select the file type. For this test, I choose an Excel file. Now I generate the Honeytoken. The Honeytoken has now been created on the Windows desktop. At this stage, Sentrix Shield is monitoring the decoy file. Now I return to Kali Linux and the active Meterpreter session. I list the files in the desktop folder. I can now see the Honeytoken file. The file name is Q4 2026 Finance Report. Because the file is monitored by Sentrix Shield, opening it should generate an alert. Now the Honeytoken trigger action is complete. I return to the Windows desktop and confirm that the file was opened. Next, I move to Gmail to inspect the alert email. In Gmail, I open the Honeytoken access alert message. This email was generated automatically by Sentrix Shield. The alert title says Honeytoken access alert. The email states that Honeytoken access was detected and requires immediate review. Now I inspect the details inside the alert. The first important field is the file path. The alert shows the file path as C users John desktop Q4 2026 finance report.xlsx. This confirms that the alert is related to the Honeytoken we created. Next, I check the host field. The host is desktop 4 VRDK84. This matches the Windows virtual machine used in the lab. Next, I check the user field. The user is John. This matches the Windows user account where the Honeytoken was opened. Next, I check the IP addresses. The alert shows IP addresses 10.0.3.15 and 10.0.2.15. This confirms the network identity of the Windows machine during the test. Next, I check the process field. The alert shows reverse lab.exe with process ID2204. This is the most important part of the investigation. The process field tells us which process opened the Honeytoken. In this lab, the Honeytoken was opened from activity connected to the reverse lab payload. This confirms that Sentrix Shield detected the decoy file access and captured the process responsible. Next, I check the access date. The alert shows the Honeytoken was accessed on June 9th, 2026 at 19:29:31 UTC. This gives us the exact time of the trigger event. The alert gives defenders useful information. This shows how deception technology can help defenders detect suspicious behavior. Honeytokens are useful because legitimate users normally should not interact with decoy files. When a Honeytoken is opened, copied, or removed, it can create a strong signal for investigation. This type of alert can help security teams respond faster. It can also help connect suspicious activity to a specific host, user, process, and timestamp. This entire demonstration was performed only inside a controlled virtual lab. Do not run these techniques against systems you do not own or do not have written permission to test. Thank you for watching.